We're back on 8.10 Taylor series manipulation, and in this section we're going to use properties of the series and power series to transform a series. So we might want to multiply two series together. Say if we want to deal with the function sine x times cosine x, we'll multiply sine x times cosine x, and we'll use the properties of series and power series to solve some complex problems. So if you recall, we have the nth Taylor polynomial, where we have, if f has n derivatives at x equal to c, then the polynomial, the nth polynomial or the nth order polynomial or the nth degree polynomial is given, where you see that green check mark, is called the nth degree Taylor polynomial for f at c, named for Brooke Taylor, an English mathematician. Then you have, if c is equal to 0, then the nth degree Taylor polynomial for f at 0 is called the nth degree Maclaurin polynomial for f, named after another English mathematician, Colin Maclaurin. So we can manipulate a Taylor and Maclaurin series in order to find this series by using the following methods: substituting, multiplying or dividing, adding or subtracting two series, differentiating or integrating a series, and multiplying or dividing the series by a constant or variable, but also multiplying a series by another series. So in this next example, I'm just going to go over it. We got through this in class. Find the first four non-zero terms of the Maclaurin series, f of x is equal to sine x cosine x. So if you don't know these already, take some time to test yourself on them. Make sure you have to memorize sine or cosine. So remember, sine is an odd function, cosine is an even function. So the exponents for the sine are odd. The exponents for the cosine function are even, as well as the factorials. So when you look at that, it's good to have a strong handle on those because you're going to need to use them without a calculator and have them memorized. So if we want to do the function, if we want to write the function series, or the series for the function that you see here, then we've got f of x is equal to sine x times cosine x, right? So then we have this part is going to represent the first four terms of the sine x, and then we have the second part is the first four terms of the cosine x. So what we're going to do then is, in multiplying them together, we're going to distribute each term of the first times each term of the second. Okay, but we're going to do something because we only want the first non-zero terms of the Maclaurin series. And remember that it's centered at 0, so we only have an x. We don't have an x minus c in the mix. Okay, so we have our x, and then we're going to multiply. Here's the first step where you see, let me get my bouncing ball here. So we have this is x times cosine, the first four terms of the cosine. Then we have the second term of sine, negative x cubed over 6 times cosine. Then we have x to the 5th over 120 times cosine. And then we have negative x to the 7th over 540 times the four terms of cosine. So what we're going to do is we're going to distribute them. And just for now, just ignore the pink that you see there. And so x times 1, x times x squared over 2, x times x to the 4th over 24, x times x to the 6th over 720, and with the appropriate signs, minus, plus, minus, an alternating series. So you have the first four terms of multiplying x, and then you do the same thing if you're multiplying the negative x cubed over 6, distribute that to the four terms. But then after you get to the third term, notice, you want to take your results of the distribution and you want to columnate your terms or your product, so that, notice I put the x cubed over 2. I'm going to put the minus x cubed over 6 directly underneath the x cubed over 2 because I'm going to add these terms together. Okay, you distribute, then you combine them all as if you were just working with a regular polynomial. Combine like terms. All right, so we have x to the 5th over 12, then distributing to the second term. The third term, then it is negative x cubed over 6 times x to the 4th over 24. It's going to give me an x to the 7th over 144. Now we continue to do this, but notice that your first term in your distribution then moves over in the columns. So you have an x to the 5th over 120 is positive. X times 1, and then x to the 5th times minus x squared over 2 is going to give you this x to the 7th over 240, but it's negative. Okay, then we're going to stop right there on that one. And then with the last one, we're going to take the negative x to the 7th over 540 times 1, and that gives us that 5040, or 5040. That gives us only one term, and that's the only thing we need. And then I'm going to take the whole enchilada. I'm going to add all 4 distributions, and I'm going to add those up together. And I add the x column, it's just x, and then I add the x cubed column. So what you see up there in pink is I'm adding, I got to get a common denominator. So if you look at 24, 12, and 120, the common denominator is 120. So I need to add the numerators and keep the 120 as the denominator. So I'm going to add these together. I start with the x cubes, bring the x down, add the x cubed over 2 and the x cubed minus x cubed, they're both negative, x cubed over 6. And so when I add those, I'll have a common denominator of 6, which is going to be 3x cubed minus 3x cubed over 6 minus x cubed over 6, which is going to give us minus 4x cubed over 6, which is going to simplify to what you see here. Okay, minus 2/3 x. And we're going to continue to do that with your x to the 5th column, where I look at the denominator is 120, that's going to be my LCD is 120, so I need to multiply 24. 24 goes into 125 times, 12 goes into 120 10 times, so I'm going to multiply the numerator by 5 on the first one, and then 10, and then I have just a 1x to the 5th for that. So with that, I end up adding them, and it turns out that I get, I can't remember how many exactly, was it 5, 15, 16 over 120, which simplifies to 2x to the 5th over 15, there, right there. Okay, and then the last column is similar. The number's a little bigger, but you want to say 720, how much does 720 go into 5040? Remember, they're factorial, so you're going to have common factors. And so I get a 7. 144 goes into 5040, 35 times, so you see that here. And then you have this last one, 240 goes into 5040, 21 times. So now you're going to add the coefficients of the x to the 7ths, and it turns out that you get 7 plus 35 plus 21 plus 1. And then you would simplify that. What do you get? 42, 62, 63, 64 over. So you would have 64 over 5040, and then you would simplify that to 4 over 315, x to the 7ths. And there's your answer. So that's one way to handle that. Probably the best way to handle it, when, especially you only need 4 terms. So you got to remember when you do your distributions, once you reach that 4th term, then you want to leave that as your marker for how far you want to go, because that gives you 4 terms, and your like terms will be placed directly underneath that, as you see. Find a Maclaurin series and the first 4 non-zero terms of f of x is equal to e to the x. Well, this one's kind of easy, and this gives another example of the series 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, so that gives you the 4 non-zero terms of e to the x. And then for e to the 2x, e to the 2x is equal to 1 plus, we're going to put 2x, replace 2x every time you see an x, plus 2x squared over 2 factorial, and then plus 2x cubed over 3 factorial. And then you're just going to simplify this. So e to the 2x, it really should say is approximately, not equal to, but approximately 1 plus 2x plus 4x squared over 2 factorial, plus 8x cubed over 3 factorial. So that if we wanted to, the thing that I like about these is that it gives you a form where you see the pattern, and if anything in math, patterns help you to solve problems, and patterns help you to get the overarching and enduring ideas and concepts that exist in math. So you see that, and when you look, or rather I should say it's a tool that helps you to see. So you have e to the x is equal to the summation from n is equal to 0 to infinity of x to the n over n factorial. So then e to the 2x is equal to then the summation from n is equal to 0 to infinity, and that's just going to be 2x to the nth power over n factorial, just replacing 2x for x. Okay, there's that one. I'll let you pause your video if you want to take a look at that better. Okay, now find a Maclaurin series for the first non-zero terms of sine squared x. So whenever I see this, I think, oh, it's probably better if I say sine squared x is equal to 1 minus cosine 2x over 2. over 2. And so what I'm going to do is use the cosine 2x. I'm going to use cosine 2x, and I'm going to rewrite cosine x with cosine 2x. So I'm going to start off like this. So this is a little aside. So cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And let's just do one more term, plus x to the 8th over 8 factorial. So I could keep going, but I just need 4 non-zero terms for f of x. So now what we're going to do is we're going to say, okay, this is, I want 1 minus cosine 2x, because that's equal to sine squared. So this is actually a pretty simple approach. So I've got 1, and then I'm going to subtract the quantity. Now I have cosine 2x, now instead of cosine x that I have put up above here. So it's going to be 1 minus, I have 2x squared over 2 factorial, plus 2x to the 4th over 4 factorial, minus 2x to the 6th over 6 factorial, and then plus, and I'm going to put this in here anyhow, plus, hold on one second, plus 2x, because you can always just kick the terms to the curb if you want. Okay, so I have that, and then this is all over. So you see, that's cosine 2x in the parentheses there. And then we have 1 minus cosine 2x here. Well, this is cosine 2x. That's this. And then over or divided by 2. Okay, so what we're going to do is do a little simplifying, but we have 1 plus a negative plus negative plus a negative. So I distributed the negative sign. Okay, and let's go back to this and see what we get. We get 1 minus cosine 2x is equal to, well, the 1's canceled, and so we have 2x So I end up with canceling these 1's. And I end up with a 4x squared over 2 factorial. So 4x squared over 2 factorial, right? Because I'm going to square the 2x. And then I have an 8 plus minus. So I'm going to subtract. I have this one. So I have minus 8 minus 2 to the 4th, which is 16x to the 4th over 4 factorial. And then it's going to be plus, and I'm thinking maybe I should probably leave the 2 in here, but it's 2 to the 6th, so 2 to the 6th is 64. So 64x to the 6th over 6 factorial. And then I have, I'll put the next one on 2 to the 8th, though, is going to be 128, 256. Gets kind of big fast. 256x to the 8th power over 8 factorial. So now let me look at those terms that I have there. So I have 2x squared, the quantity, over 2 factorial. Got it. And then the 16x to the 4th over 4 factorial. Okay, and then remember that this is all divided by 2. So each one of these terms divided by 2. Okay, so we could actually simplify this a little quicker, but I'm going to leave it like this. So when you divide it by 2, that 2 is going to go into the numerator. I'm going to leave the factorial alone, and the 2 is going to go into the 4 in the first term. So you're going to divide the 2. The 4 is going to be 2x squared over 2 factorial minus, then this is going to become 8x to the 4th over 4 factorial. And this is going to be, the 2 is going to go into 64 minus 32x to the 6th over 6 factorial. And then minus, oh, that's going to be a plus minus then this is going to be 2 goes into 256, 128x to the 8th over 8 factorial. Okay. And so we have our series set up. And there it is. There you go. There you have it. This is then going to be your 1 minus cosine 2x over 2 series. And it simplifies like that. Okay, I'm going to stop the video at this point because it's getting a little bit long, and I'll pick up with example 4. Have a great day.